quite surprised that everyone is still here. You didn't run away. Okay, we're lucky. Okay, so everybody, I'm Tommaso Cucinotta. I'm associate professor at the Real-Time Systems Lab of Scuola Superiore Sant'Anna University in Pisa. You heard the university, I guess. Here, I still like to keep the additional affiliation I had temporarily last year, because I've been a visiting professor in Sweden, in Mälardalens University, Sweden. As basically these things I've been doing both last year, presented the last year OSPM and this year also, are basically things that came up during, basically for research needs. In some joint projects we've been carrying out with them. So. Okay, so I'm going to talk about improving schedule deadline wake-up rule in presence of microsleeps. And as I'm quite sure, like here, everyone knows about schedule deadline. So let's just refresh a little bit the situation. So as you know, in the Linux kernel, you can set a schedule deadline scheduling class for real-time tasks that basically uses three static parameters, which are budget, runtime, also known as budget, relative deadline and period. And the meaning of that is basically that you want, when you go schedule deadline, you would like the kernel to guarantee to this thread runtime time on the CPU within the deadline for when you are ready to run, and this should ideally be repeatable every period. So you want the guarantee of having runtime execution time on the CPU within the deadline every period. Normally, this is situation you might have runtime lower than deadline, lower than period, albeit very often we also see deadline equals period in various scenarios. These are the three static parameters please.
Sorry, super basic question, because I've never actually used this. Do you have control as a user over when the period starts of the kind of alignment?
Yeah. So that you can control when the period starts basically by, if you just wait for a sufficient amount of time. For example, if you wait for a whole period, then you are sure that the period the kernel will be aligned exactly to when the application, the user space, the process wakes up. Not when it gets scheduled, but when it wakes up. Okay, so same goes if you've been idle for sufficient time and you're woken up by receiving a packet, it all starts. It gets reset from the moment you get woken up. Same goes with the timer. So if you really want, you can also synchronize multiple threads. You can stagger them as you need on multi-cores and do a bunch of things. But okay, so the scheduler works by using having two dynamic parameters that are carried out and evolved and updated automatically by the scheduler as the process, as each thread gets scheduled. These are the current runtime, so runtime left, basically, and the current absolute deadline. So the thing is that if the thread tries to overrun the runtime, it gets throttled. So the idea is that, of course, while we schedule thread on the CPU, we just decrease the runtime left. When it goes to 0, it's over. You get throttled till the next period. Threads are scheduled by earliest deadline first in the end. Deadline threads scheduled by earliest deadline first. That can be configured as a global EDF scheduler. It can be a partitioned EDF scheduler. If you like, you can configure multiple clustered global CPU scheduling subdomains if you configure CPU sets properly. Just still as a background on schedule deadline, the two main characteristics of schedule deadlines is that it's not only an EDF scheduler, but it also implements this constant bandwidth server that guarantees temporal isolation among tasks, in the sense that if you have tasks that will misbehave trying to do things that they should not be doing, they basically can only affect the timing of themselves. they won't be affecting the timing of other tasks that are actually behaving according to the model. The model is very simple. If you have the need to run for a runtime by deadline every period, that means once you begin running, you should be continuously backlogged. You should not be sleeping, or you should not be doing I/O suspending or whatever. Should be doing some processing, some computation, and then once you're done, you go back to sleep. That's what you should do ideally. If you don't do that and misbehave, then you can do like a couple of scenarios we can see here. This is an example of 2 tasks on the same CPUs where, with the utilization that basically fits within the CPU. This is runtime over deadline equals period. And in this case, as an example, a bad job that tries to run for too long, so tries to overrun the runtime. If you don't stop it, then of course you might have that this job in the end ends within its own period and deadline, but another job may actually miss its period of deadline. The other case is the one we see. So the picture on the down here on the bottom is what schedulability does. If you declared that you needed 5, could be whatever, but 5 units, let's say milliseconds of runtime. Once you reach the 5 milliseconds runtime, you are stopped. Instead of left running, you are stopped, and then you are resumed at the next period where your budget is refilled. On the right, there is the other misbehavior, which happens if you block. If instead of being continuously backlogged, you block. So this is a very simple example. Task begins its period, then it blocks. Then basically at last moment, it wakes back up. And if you leave the task with the same deadline, basically you will have, the only way that this task can meet its deadline is to continuously run. But there are other tasks in the system. So either it will miss deadline, or as in this picture, you will have someone else missing the deadline because you blocked and then you resumed in the same instance. So you should not be doing that. But with the scheduled deadline, what we do is, well, after you block and once you unblock, basically there is the wake up rule of the CBS, the wake up rule, that in this case resets the deadline parameters of the tasks that is misbehaving. And so basically pushes this deadline forward of 1 period. And this basically is allowing the schedule to correctly schedule the second task. So again, the other task that is behaving correctly is not affected by the misbehaving task. And these 2 things, we need both to make temporal isolation. If you want more information, this is well explained in the documentation, TXT, in the scheduled TXT file in the kernel tree. There's also this article where these pictures come from. It's a very old article from an LWN post that we did a long time ago that basically explains the very basic things. Okay. So as we said, we need these 2 methods. And what if we get into the specifics of the wake-up rule of the CBS? What happens is that basically we may have 2 situations. Either when we wake up, the runtime left, if I take the runtime left till the deadline divided by the time I have available from the wake-up moment till the deadline, if I do this division, either this number comes out to be lower than the bandwidth of the task, which is the static runtime divided by deadline period, or it is higher than that. So if it's lower, basically we have no problems. We can keep the current runtime and deadline parameters of the task. But if it's higher, which happens in this case here, you see in this case, this was a task that had a utilization of 5/9. When it wakes up here, the time to deadline is equal to the runtime left. So it would need a bandwidth of 1, a logical bandwidth of the CPU of 1. So it's too much compared to the 5/9, which was granted by the kernel. So in this situation, deadline applies the wake-up rule that is very simple, reset parameters. So runtime left is refilled to the static filled up runtime, and the deadline is shifted 1 period apart, which is exactly what is done in this picture here. Okay, however, that schedule implements also an alternative wake-up rule, which is we call some papers the revised wake-up rule. That says that basically tries to address address this problem that sometimes for some applications this reset of the deadline and this reset of basically of the periodicity of the task may not be desirable. And that happens, for example, in the major use case I'm focusing in this talk. Like imagine I have a micro sleep because for whatever reason, while I was running, I take a mutex, which is locked by someone else, but I sleep for a very small time, then I wake up. Then in this case, if I'm in that case in that case of the reset, then my deadline gets postponed. And maybe that's not desirable because I had originally a deadline, I wanted to keep the original deadline. So there's these other mechanisms that was designed over the years that basically says, okay, if you want to keep your current deadline, we can have this alternative behavior, the revised wake-up rule, where we want to keep the current deadline, but if we keep the current absolute deadline without changing it, then the thing is that we cannot have the runtime left divided to time to absolute deadline greater than the original bandwidth that was statically configured for the task. So that means that if the runtime left is too much, we need to decrease it. So that means instead of postponing the deadline and refilling the budget to full budget, we actually keep the current absolute deadline and possibly we slash the runtime left. We just use the runtime left that is the minimum, the maximum one that is allowed to satisfy this condition, which is roughly what you have here and below. Okay, so actually scheduling chooses between these two behaviors of the wake-up rule in a little bit of a fancy way at the moment. So if the deadline, the statically configured deadline is equal to the period, then scheduling uses the original wake-up rule with the reset and deadline postponement. Instead, if deadline is different from the period, we use the revised wake-up rule. And this is not even documented in documentation schedulability.txt. So actually, this is only documented in the Git commit log by Daniels, where there's a very long explanation where Daniel actually explains where this comes from. It's a sort of security or robustness feature of the scheduler.
Someone might submit a patch to add it to documentation.
Could be, yeah, might be useful. Yeah, of course, Daniel unfortunately couldn't do the patch, but yeah. So anyway, this is how this is working today. So you cannot choose between the two, but if you want, you can choose by setting deadline equals period plus 1 nanosecond, which is a fancy way of choosing the behavior. So anyway, what is the problem of this mechanism? As it is now, if a task has a micro sleep, as I said, and here I'm showing a task that is running, what I'm showing on this plot is on the x-axis time, on the y-axis the runtime left, and I'm showing the runtime left that is measured continuously by continuously logged task that is just CPU intensively computing and just retrieving the runtime left using the sched_get_attr new feature we had I showed in the last OSPM last year that is now should appear sometime soon in the mainline kernel. So I'm reading the runtime left, and at some point, actually, I decide to sleep. In this simple application, I did a micro sleep, but I could have been suspended for whatever reason. So in this case, I'm suspending for 5 milliseconds, and in the left picture, this is the case where basically I am scheduled on the CPU immediately because maybe the second task that is also a deadline task on the same CPU. The second task has a deadline that is a little bit higher than mine. So I go first, then I do the suspension. During the suspension, the other task actually takes advantage and is scheduled for 5 milliseconds because it's ready to run. Then I resume, and according to schedule deadline, I can keep my leftover budget and my current deadline, which is here at 100 milliseconds. And I keep going till I do whatever I have to do. Here I get throttled, or maybe I finished whatever it is, the other task gets scheduled, I will happily finish before its deadline, hopefully, okay. Now, on the right picture, we have a situation that is slightly different. So these two tasks have the same parameters, 50 milliseconds runtime, 100 milliseconds deadline equals period. Only that on the right picture, I may build the scenario in such a way that the second task actually has a deadline that is slightly lower than the deadline on the former task. So in this case, the other task goes first. Once it's done, I go on the CPU here. Once I go on the CPU, now I'm in that case when I sleep and I wake up. Once I wake up here, I'm in that situation where my leftover runtime is too much compared to what was my, this 50% that was formerly granted, as a static reservation for my task. So in this case, the revised wake-up rule, as I'm forcing here the use of the revised wake-up rule, tells me, okay, I'll be keeping my own deadline, but my runtime will be slashed according to what is needed to preserve the original computational bandwidth of the task. In this example we are showing, which I did really on a real, this is plot of the real budget coming from, as I said, from these two tasks running in a simple program with two threads. They get deployed on the same CPU, which get deadline. For a 5 millisecond sleep on the right, I get my budget cut by 15 milliseconds. Just an example, but I can build it as I want. So this is just a little bit a zoom of this situation. And again, left side, when I sleep and then wake up, my what is called virtual time is in the future. So that means I've been scheduled. I've already eaten a lot of runtime before blocking, but when I unblock, I have little runtime left. Schedule deadline says, yeah, okay, keep going, it's safe. On the right side is the one when I unblock and schedule deadline says, no, you have too much budget left here for given if you want to keep the deadline, so I will slash your deadline. Here I lose 15 milliseconds for a 5 millisecond sleep. I can do, I had also another example. This is another second example where actually I'm losing for the same 5 millisecond sleep. If I do it earlier in the instance, in this case, I'm losing 20 milliseconds, whatever it is. Yeah, it's bigger. You can see it's bigger gap in this case. It's even worse. So, okay, so what we need to fix this situation, because we have a problem. Okay, this budget slash was coming from a theoretical condition, but actually, as we do in academia, reviewing the theory, turns out that maybe we're being a little bit too much conservative. We can clearly do something better. I'm sorry to say it's obvious that we can do something better than slashing the budget, because for a 5 millisecond sleep, what we can do, we can simply compare the safe budget we have from this theory with, okay, what if we simply had been running for those 5 milliseconds of blocking time? I mean, we could have run without breaking anything. That's the EDF theory from the 60s. We could have run without breaking anything, and we would have consumed only the 5 milliseconds for which we've been blocked. So that means that if on wake up, I reduce my runtime by the blocking time, that's safe. It has to be safe. It satisfies all the theory, that's the problem. And this is actually what we can do with a very small patch. Don't look really at the code because this has at least one bug I'm aware of, but it's the minimum that is needed to let the experiment I'm going to show you work, because this is, basically what we can obtain is this one with a revised, with a fixed revised wake up rule. Well, you can see, I mean, simply the line keeps going linearly as usual. That means I sleep for 5 milliseconds. When I wake up after 5 milliseconds, I lost 5 milliseconds in this case. So what the code actually does is to compare the the budget I get from subtracting the blocking time with the budget computed by the original revised wake-up rule, which is what we have today in the kernel, and actually takes the better of the two. Yeah, so yeah, this is the other case, a second case where I was losing what is 20 milliseconds, right? And actually we can fix it by losing only 5 milliseconds of budget, and so scheduling tasks can be happier with this fixed wake-up rule. So this rule looks like, I mean, it is safer under all scenarios like the former one in terms of schedulability analysis. So we don't break temporal isolation, we don't break anything. Actually, it may be a little bit pessimistic still if we have deadline inheritance scenarios, because when we wake up and we subtract the processing time, we subtract the blocking time of the task. This is, so imagine the case where I didn't block. If I were continuously running, then I would have consumed my budget only if I had been for the whole blocking time, if I had been the eligible task with the earliest deadline on the CPU. But if there had been another task, maybe coming here with a shorter deadline preempting me, and that task would have consumed its own budget. So that means that in that case, I should not have consumed the blocking time. I mean, that time should not have been subtracted by the budget. So in other words, this subtracting the blocking time is again conservative. I may even slash too much the budget in this case, but it's a lot better than earlier, especially in cases, as I said, of microsleeps, little mutexes, where you block for a little time, wake up, and I guess these are very commonplace. So that means that we could do some further improvement if we really wanted, but maybe it's more complicated, so it's probably not worth this. Yeah, and what else? Yeah, in case of deadline inheritance, also the fact is that I might have blocked, but actually if I blocked on a mutex held by a lock owner that actually has been scheduled in place of me during the blocking time, that means that the lock owner actually has already subtracted my budget due to the way we do bandwidth inheritance. But you know better what we have in deadline today.
We should do that.
We should do that. So we should subtract the running time not to the lock owner, but to the higher priority thread. So the earliest deadline thread that is actually waiting for you to finish. So in that case, basically, I have already subtracted the runtime. So when I wake up, I subtract the blocking time. So I do it twice. I risk doing it twice. Okay, don't know if I've been clear. Again, if I do it twice, it's safer than, I mean, it doesn't break anything. So in a sense, it's okay. Anyway, it's better than it is now. It's very simple. Instead, the tracking if there was any deadline inheritance becomes more complicated, but maybe we can sort it out later. In terms of implementation, as I said, basically, the only information I need is to know when we wake up. We need to know what was the time in which we blocked. We've been the scheduled. So I thought initially to use, or I tried to use the sched stats block start or sleep start, block start. But then, yeah, you rightfully pointed out, okay, that may not be always enabled, maybe it gets disabled, whatever. So I said, okay, let's use the XX start instead. That despite its name, XX start, it's also updated when we dequeue the task, so it tracks the timestamp of the dequeuing. And luckily, in this moment in the scheduler code, we didn't screw it up yet when we get executed again. So it still contains the right information. But yeah, testing of this patch is something, I mean, for now, I say don't look too much at the code. So basically we are even reusing the same variables we already have in the kernel. We're not even adding a single field to the task structure or to the scheduling entity or whatever to do this. And yeah, so, okay. If we wanted to fix the pessimism we have in this technique, the pessimism could be addressed by basically tracking if during the blocking time of the task I've been actually the task eligible for to be scheduled. But if you take the theoretical scenario that's been analyzed in a paper published at RTNS, it's already a decade ago. So here, but it requires a second red black trade. So there was a prototype implementation by Alessio Barsini. Some of you know him, and problem is that there's a lot of complexity behind that. And after all, especially if I have a small sleep, where this is mostly used for, if I have a small sleep, the probability that in there's few milliseconds of sleep or maybe even 100 microseconds of sleep, I get another deadline task coming, preempting, and then with a shorter deadline than 100 microseconds. I mean, it's quite unlikely. So, but I mean, we have a theoretical fix that probably would be quite complicated to get in. So maybe just subtracting the blocking time could be good enough. So to conclude, just the proposal is to have this simple fix to the schedule deadline revised wake-up rule, avoiding unneeded runtime slashes or microsleeps. We keep the original temporary solution property without breaking anything. Further runtime, maybe we don't need to enhance it further. Maybe deadline inheritance also could be interesting to look at that. Perhaps it becomes more complicated to track deadline inheritance cases rather than not. And anyway, we are still conservative again, so maybe it's already good enough. The other things I wanted to mention is that for now, just we have this decision in schedule deadline between the revised wake up versus the original self-synchronizing wake up rule, resetting wake up rule of the CBS that is done based on whether the deadline is equal, the static deadline is equal to the period or not. So that means that, for example, to run these use cases where actually I wanted to run with deadline equals period, what I did was actually to set deadline period equals deadline plus 1 nanosecond or something like that. Yeah, really plus 1 to, which is a weird API if you pass me the term API. So the thing would be, okay, maybe probably a nicer way API wise would be to have a flag, another flag in the sched set ATTR syscall, where we can set the flag and request the behavior. So we want to go for the wake up rule, and instead, the wake up rule, the proposal would be to just update it with this new improved rule that is better than the other one. So there's no reason, we don't see a reason to choose between. We don't have a choose of 3. We have just choose of two, either all the CBS, traditional CBS, or the. Yeah, and maybe another thing I forgot here to mention is didn't think at all about DBFS actually. I'm not sure if that dimension adds any, but yeah.
I don't think that changes because we only use the bandwidth indication. So if
I don't know if the blocking time we subtract, we should we scale, but maybe we think, probably not. Okay. Anyway, that's all. Thanks for listening.
I actually got a question. Who wouldn't be using actually the revised wake up rule?
Would not be using.
So why using the more pessimistic one?
So the deadline, so the original CBS rule has always had this nice property of self-synchronizing itself. So the thing is that depending on how your application is done, you can be okay if you have a periodic application.
Maybe it goes back to what Ryan asked, that if you're using sleeps for actually synchronizing with the period, and
we still have the behavior even with the
if you are,
but you have to sleep for at least a period to be sure. As deadline works today with the default CBS rule, maybe you can just self-synchronizing even. It's just, you for example, receive a packet, get woken up, you have till your period equals deadline and you have runtime granted. Maybe use less than that, you go to sleep, then after a while you get again woken up. Indeed, you might get again the same, from when you woken up, you get reset. But with the wake up rule, you keep the original deadline, and it's so it depends on probably, I guess, your application, how it's done now.
I would just one.
So there was probably any other curiosities, questions about deadline? I should have mentioned the keyword. Yeah, sorry, please.
Does the application have a way to know if it missed the deadline, and so it can maybe do less work?
Yeah, sorry, that was part of the background. So we have 3 flags at the moment that you can associate with scheduled deadline reservation. The 3 flags are, one is to be delivered a signal in case you overrun the runtime, but if you overrun the runtime, you certainly missed the deadline. And let's say, from the kernel viewpoint, the kernel doesn't really know what you're doing in user space. So the kernel principally has no clue about what is your application level deadline, how it is set. So the only thing that can do the kernel is, look, you've been trying to overrun the runtime. So when you get throttled, when you get unthrottled, then you run again, you get a signal, and at least application level, the signal handler say, I did something, you can ignore it or use it, or that's one thing. And then there are, other flags are if you actually, after runtime, if you want opportunistically the kernel to give you more runtime than what you asked for, so you can have the static guaranteed plus something more that gets given to you in a greedy fashion. So let's say if you are the lucky one, you get more runtime dynamically. This is the group algorithm. It's a greedy reclamation of unused bandwidth. You can enable that with the schedule reclaim flag. And there's a third flag that addresses the issue that normally a scheduled deadline task cannot fork, cannot clone itself, cannot create a thread, because in the child we would need to make a schedulability check, the schedule, the analysis check on pthread create, which is not really something very. So basically what was done was that by default, the scheduled deadline task cannot try. If you try to pthread create, it fails, or fork, it fails, unless you set this flag. And this flag basically means any child would be scheduled.
It would reset to the default, I guess.
Yeah, to the default, to scheduled. Or I'm not sure if schedXT today, but whatever.
So in the
scheduled and become. Unless you run in partial mode.
Yeah. You add the interface, the modification to the schedule, so maybe you can also retrieve.
And you can retrieve the parameters. You can retrieve today with the they'll have it here. So what I did here, I did this modified the sched get attr syscall, where the last parameter of the syscall is a flags parameter that should be mandated to 0 according to the man page. Now it can be 1. If you set it to 1, it means I don't want the static parameters. Thanks. Normally I should have it as, but I can retrieve the instantaneous one, so the runtime left, and I can retrieve the absolute deadline. Now, these two information, if I really wanted, this was the thing presented last OSPM. These two information were available in a way also somewhat in the procfs. If you really wanted, you could go and read the procfs. If you're a deadline task, you would see runtime and deadline, but with two big problems. So the first one is that the runtime, when you read it from procfs, doesn't get updated. You don't go to update deadline, whatever, and so it doesn't reflect your actual runtime left. It only reflects the last time that the scheduler was called and it updated your runtime. So it's not actually accurate. Maybe it's accurate hertz. It has a hertz precision at least. Instead, and the problem of the deadline is that if you read the flag, the deadline field from procfs, it's the run queue clock time. So it's the deadline run queue clock time. Normally, you don't do much from user space. Okay, you can debug, but besides debugging, you don't do much from user space. Instead, in this syscall, we have, once we set the last flags to 1, we get the deadline reshaped offset into clock monotonic time reference. So we can do something with that information. Like, I mean, we can compare it with our deadlines. We can compare it with whatever we want. And we know we may be aware of where the deadline that the kernel has set for us is compared to what is my own timing as a task, my start time, period, deadline, whatever I need.
Other questions?
Other questions?
All right.
All right.
I think so. Thank you.
Okay. Thank you.